So let's go over another, basically different way of phrasing the problem. What's the likelihood that basically we get a match of, or we get two people of having the same birthday? And that's what we were checking over here. Um, could say has two match, because what we're going to program now is has three match, which we could do by doing the same kind of thing. So that's basically what is the likelihood that given a room full of n number of people, that three of them share a birthday. And we could do that by basically doing this, looking two ahead instead of one ahead. In fact, that's probably a very easy way. That's a fairly straightforward way to do it. Okay. 3 matches 2. If has, and let's switch this up to make it match. Now, I can't start a variable with a number, that's why I'm switching it up. So has match 2, has match 3. And so that's two people having the same number birthday. Has match 2. Has match 3. And we want to use the same. It's probably useful to use the same trials over here. So check the same one generated list rather than generating a new one. And so what we can do over here is now print this. Actually, let's go ahead and clean it up a bit. So the separator is equal to tab rather than ending with a space. And now we just change this to matches 3. And let it run, and it's going to take a bit longer because we've got to doing twice the number of checks. So with 23 people, there's a 12% chance that wait, no, that's not 12. That's 1% chance. There's a 1% chance that that basically all of them match. But let's go ahead and boot this up to 50. So with 50, we're seeing basically 97% chance. Yep, 97% chance. And now we're up to 12% over here. So 50 people, there's a 12% chance. So let's say with our class size, which is about 100, let's say there's 100 of you who show up to the online lectures. So that's the number I typically look for. And let's go ahead and see this now. It takes a bit longer because the list is bigger. Hundred people didn't have a match. But with 100 people, there's a 64% chance that if one of you says, it's my birthday, that two other people are going to go, oh, it's my birthday too. That's insane. Or rather, maybe that's a bad way to phrase it, but there's two. But basically, that's a pretty crazy way of just think about it. Like, grab 100 people. 65% chance of 3 people sharing the same birthday. We could go up some more, but let's go ahead and just take a look that maybe will be a bit quicker. Instead, what we're trying, another way of phrasing, of looking at this, is we are trying to see basically, we can generalize this out and basically ask ourselves, hey, we've got n people. Can we see how many if we've got n matches? Or can we see the numbers of people we have? Or the numbers we have just kind of all together, nice and easy to see. So let's go ahead and take a look at this. Num has match. And this one's going to be the nice and general one. Birthdays list, and I'm going to have a default n is equal to 2. So what this does over here is that I have a variable n, and if I don't provide one, it's going to automatically be 2. That's what this does. This is what we call a default variable. And it's basically saying, hey, you can provide an n, but if you don't, it's just going to be 2. Right? And what we're going to do here is, rather than sorting our list, we're going to create a dictionary, right? Because we're counting the number of number of occurrences of each birthday. So bday count. Okay, for b in birthdays, if b in bday count. So in other words, if we've seen this birthday before, great. Then we've seen it one more time, so bday count of this particular birthday is equal to plus equals 1. So no need to overcomplicate it. Just that we've seen it one more time. Otherwise, this is the first time we've seen it. Whoops. Otherwise, this is the first time we've seen it. So bday count of this birthday is equal to 1. So if we've seen it, add 1 to the number of times we've seen it. If we haven't seen it, I've just seen it once. And now we can say for bday in bday count. For every birthday in the birthday count, and basically what I'm going to do is I'm going to ask how many we have. So for so occurrences is equal to bday count. Remember, so this will go through all the keys. So this will go through all the birthdays that have been registered. And we'll say that's the number of occurrences we have. Okay, so that's the number of occurrences we have. So now what? Well, we have now we can just simply say, hey, if this number of occurrences is greater than or equal to the n that I set up, return true. And then if I get all the way to the end, return false. So we can now basically use one function to do all this. Matches is equal to 0. If bday count, if has match bday count, has match bdays. If there's a match in the birthdays, matches plus equals 1. Print matches divided by trials for a percentage. Okay. And we're computing, and hopefully not messing up horribly. Right, with a list of 100 people, that takes a while, and we've got 1. So let's go down to a known value, 23. 23 people should be around 50%. Boom. Okay, but now I can specify, hey, what if I'm looking for matches of 3? This shouldn't take any longer. There's our 1%. What if I was looking for matches where basically, what if, what's the odds that if I have 23 people in the room, 4 of them share the same birthday? Non-zero. So 1 out of 5,000 times, apparently. Which is not nothing, but I wouldn't bet on that. In fact, in a room of 300 people, let's go ahead and lower this to 1,000 trials, just because 300, room of 300 people, though, 98%. Wow. So in a room of 300 people, there's a 98% chance that 4 of them share a birthday. That's pretty shocking. But the math holds out on this. But we don't need to check the math because we're simulating it, which is nice and fine.